So section 7.4 is going to just cover bootstrapping, and I'm not going to give you a real intense covering of bootstrapping, but we are going to at least introduce it and give you an example to have some fun with it. Now, the reason we're considering bootstrapping here is because it's an example of a non-parametric method. So let's remind ourselves about the difference between a parameter and a statistic. So what would some examples of parameters be? Anyone? What do we got here? What would I list under parameters? What would be perfect? Mu, sigma, and p. Those are our parameters for the mean, standard deviation, and population proportion. What are the associated statistics? Someone else. What are the associated statistics? What statistic goes with the mean? X bar. Thank you. Thank you, Zach. How about the standard deviation? S. And the population proportion? It's not P, but it's P hat. Yeah. P chapeau. I don't know why I always like saying that, but I do. All right. Well done. And thank you, Sonia. Now, typically speaking, when you collect some data, you get a sample statistic. A sample statistic is a summary value of a set of sample data. What distinguishes a statistic from a population or from a parameter? Why do I have two sets of symbols? Perfect. Parameters are numerical characteristics of an entire population. So that if you had data from everything that you're interested in studying in, then you can calculate a parameter. Mean, standard deviation, proportion, whatever. But if you've only got a sample, then you're going to get a statistic. Now, the thing is, we're hoping this statistic is a good estimate of our population parameter. It may be, it may not be. But either way, that sample statistic is a point estimate. It's just one value. And you know going in that it's probably not the exact value of your population parameter. So what do? You surround it by a confidence interval. You say, well, it could be a little bit lower, it could be a little bit higher. We think it's in this range. We're confident, 95% confident, 9% confident, 99% confident that it's within this interval. So we create a confidence interval around this, and then we hope that our parameter is going to be in that interval. And maybe, it may not be. Now, we had several methods for working on these things. It kind of depended on what parameter you're working with. If you're dealing with population proportion and our sample estimates of that was in section 7.1. And we could construct a confidence interval that way. We could also do something here for section 7.2 would be our confidence interval estimates for the population mean. And in section 7.3, we had confidence interval estimates for not only the standard deviation, but the variance. And the variance is just the square of the standard deviation. Sorry about that. Thank you. So you had to assume that you had a large sample size that is greater than 30, or that you're sampling from a normal population. Now, if you're sampling from a normal population, that means that that population has some mean and standard deviation. So it's distributed normally with a mean of mu and a standard deviation of sigma. In other words, it depends on parameters. It depends on certain assumptions. And it'd be nice if we didn't have to always make those assumptions. So that's why we use what are called non-parametric assumptions or non-parametric methods, because they don't require these assumptions. And it's a different way to try and get the same information. So let's do that with one of the problems from the book. I just want to check back here. Did it sign me out? You dog. Let's see. No, not there. Not there. Oh, man. All right. Oh, no. All right. I guess I'm going to have to go about this a long way. Content. I apologize. I was like so happy that I'm like, oh, I got this all set up. And of course, no. So this is going to be on page 364, I think. Let me just get there. Pearson text. This would be nice to have the pause button here for my video right now, but I don't have that. 7. End of chapter materials, and then we'll just back up. There we go. We're going to talk about brain volume. So the data set that you should have in StatDisk right now is this one. It says usually brain volume is measured from data set 12. Use a bootstrap method with 1,000 bootstrap samples. So in our typical way to approach this in terms of a confidence interval, you have to be able to assume that this has a normal distribution. That is, we're taking this data from a population which has a normal distribution. That may or may not be the case. You can test this to see if it does have a normal distribution, or we can reject that hypothesis. But this is such a small data set that it's kind of tough to do that. So let's approach it a different way. And here's what's going to happen. We're going to take our 20 values here and throw them back in a hat and then pull out 20 samples. Now, if we sampled without replacement, we would just get this sample again and again and again. So here's the trick. When we sample and resample this, we're going to sample with replacement. So you're going to take 20 random pulls out of this, and you can pull out the same number all 20 times if you get really, really lucky. Or you can pull out the same number 19 times, whatever. But you can pull out any of these values at any one time. And when we do that, we're going to calculate the mean and standard deviation for that sample. Okay. After we do that, then we'll have lots and lots of samples from this distribution. And we're just going to look at the 97.5 percentile and the 2.5 percentile. Basically, we're going to throw out the outside 2.5% on either end and just keep what's in the middle. And that's going to be our 95% confidence interval. So how do I do that? Well, let's take a look here. Resampling. So we're going to go to Bootstrap 1 mean. So underneath the resampling menu, pick Bootstrap 1 mean. It should give you a column like this. And it's going to ask you, well, how many resamplings do you want to do? Well, let's do a lot of them. Let's do 1,000 resamplings. So we're going to sample 20 samples from this distribution, or 20 samples from this data set, 1,000 times. And for each 1,000 times, we're going to calculate the mean and standard deviation. So there's not a whole lot for you to do here. This is a lot of work for the computer to do, though. Let's click Evaluate. Now let me tell you that your numbers are going to be different than mine. because each of us is seeing this happen at random. But the overall result should be kind of similar for all of us. And let's take a look at what's going on here. If you look, it gives us a list of what's called sorted means. So you can scroll down. And what's happening to the numbers as I scroll down? Yeah, they're increasing. Thank you. And you can scroll down and down and down. In fact, you can go all the way to the bottom, and you'll see that we have exactly 1,000 of these things. So what the 95% confidence interval is going to do is it's going to say, all right, I want the middle 95%. So graphically speaking, here's 0, here's 100. Your 95% confidence interval comes by throwing off the bottom 2.5% here and the top 2.5% here. Your 95% confidence interval is going to be everything in between here. I should put percentile. So where are those values? Well, we can get that from StatDisk. Let's take a look back here. Right here. Our upper confidence interval, let's see. Oh, excuse me, our lower confidence interval is 1069.2. 1069.2. And the upper one is 1184.8. That's your confidence interval for this one. Now, you likely got something that looks a little bit different, and that's okay. Nothing wrong with that. When I did it earlier this morning for my other class, these are the numbers I got. They're similar, but they're not. They're similar, but they're not exact. 1073.9 to 1181.65. Okay, but this is your confidence interval. It's a different way at getting at a similar result. And what you can do from here is you can build up a conclusion. You can state this in exactly the same way that we did before. This is kind of cookie cutter stuff, right? We can be 95% confident that the true mean value or mean brain volume is between 1069.2 and 1184.8. I believe the units are cubic centimeters. So, hey, that's where we think that the mean value, the true mean value is, if we could somehow calculate that for everybody in our population. Now, brain volume is often used to help distinguish amongst various different things in anthropology, like Neanderthals versus Homo habilis versus Homo erectus, Homo sapiens, etc. So brain volume is kind of a big thing. And it's an interesting, I don't think it's a completely resolved question as to whether or not Neanderthals just died out or were they eventually interbred with Homo sapiens. I think the latter, and I think that's where the research is leading. But in any case, are you comfortable with that part right there? Are you able to get that? Now, I'm not going to test you exactly on this, but you should be able to write conclusions. You should know, for instance, why we use a non-parametric method. But before I discuss that, let's follow up with this a little bit more and do one last thing. Suppose we're actually able to make the assumption that this population that we're sampling from has a normal distribution. If that's the case, then we could use a parametric method. Let's see how our parametric method would compare to the non-parametric method. So for the parametric method, you're going to click Analysis, then Confidence Interval, and mean one sample. So Analysis, Confidence Interval, mean one sample. Now our data is going to be in column 1, so click Use Data. We still want a 95% confidence interval. Now they've given column 1 an actual name. That name is original, so I'll click there. It's going to use the t-distribution to create this confidence interval. So there you go. 1067.47 to 1184.42. So let me just write those numbers down. How did your numbers compare to mine? Were they similar? You got the exact same? Really? Oh, yeah. This one you did, but the previous one, no. When we did the bootstrapping? Got the exact same? Oh, okay. Yeah, I wouldn't think you would get the exact same on the other one, but this one you should, and I'm glad to hear that. That's good. Yeah, very similar. Thank you. Good. All right, so let me just write down these values just for reference sake. So that was versus 1067.48 to 1184.42. And that's if we use the methods from section 7.2. Okay, so nice. It gives you an alternative to the old, well, let's just assume that it's a normal population. It might not be. In fact, all the years I've been teaching, seldom do I ever see a normal distribution in terms of your test scores. I never get that nice little hump in the middle with few out in front, few out in back. It just never, ever happens. So, now, one of the things that I would want you to know is the advantage of a non-parametric method. The advantage of a non-parametric method is that it doesn't require many assumptions about your data. So the advantage of a non-parametric method is that it doesn't require many assumptions about your data. Yay, and that's good to know. Now, there are some downsides. It depends on the non-parametric test. And we're going to spend some more time at the end of the semester working on non-parametric methods. We'll do the sign test. We'll do maybe the Wilcoxon rank sum test, etc. But, you know, the advantage here is that you don't have to assume things about your distribution. Like, gee, it has to be normal, or n is greater than 30. And there's a whole list of assumptions that we just don't have to make. Now, the downside is that it's not always as powerful, especially if there is really a normal population that underlies your data or something like that. But, you know, for the small things that we need to do, yeah, it's not too bad. It's actually pretty handy. So, any questions or comments on this one? Okay, cool.